Welcome to another video on the hoop stress and the axial stress in the case of vertical pipe that is filled with the water. So this one is a vertical pipe which one is open to the atmosphere and is filled with water, and the total height of the water will be equal to h. Di represents here the internal diameter and T represents the thickness. So DO will be equal to Di plus 2 times of T. Now this surface is open to the atmosphere. So the gauge pressure at the top will be equal to 0. And in the case of liquids, the gauge pressure P is given as the product of density multiplied by G multiplied by H, where H is a depth. So the depth is 0 on the top surface, so pressure will also equal to 0, and the depth is maximum at the bottom, that equal to capital H. And the product of rho and G is a constant here, so pressure is proportional to H. If the pressure is proportional to H, it means that we can show the variation of pressure from the top, that is at A, to bottom at B, and this variation taking place in a linear way. So the gauge pressure at point A will be equal to 0, and the gauge pressure at point B will be maximum value. We will denote here equal to P maximum, and is equal to product of density multiplied by G multiplied by capital H, and this variation takes place in a straight line form. So this one is representing the pressure distribution in the column of height equal to H. So in the case of vertical standpipe, the hoop stresses and the longitudinal or axial stresses are two types of stresses that can occur. The hoop stress, also known as the circumferential stress, is that stress that occurs on the circumferential direction of a cylindrical object like standpipe, is caused by the internal pressure P, and the pressure is since variable. We will find here the pressure at point A equal to 0. So the hoop stress at point A will also equal to 0. The hoop stress at the top, that is at point A, since we have pressure at A will be equal to 0, the hoop stress is also equal to 0. So we have sigma H at point A will be equal to pressure multiplied by diameter divided by 2 times of thickness will be equal to 0, as the pressure will be equal to 0 at point A. But the hoop stress is maximum at point B, and we have, so the hoop stress at bottom point B, where we have pressure is equal to PB, which one is maximum pressure, is given as product of rho multiplied by G multiplied by the column H. So corresponding hoop stress will be maximum at bottom point. So we have corresponding hoop stress will be sigma HB will be equal to the pressure at point B multiplied by diameter D, that is the internal diameter Di. So let's make it equal to Di, and is further divided by 2 times of thickness T. And if you are interested at the mid depth, let's say at point C, at mid depth we have, that is the column will be equal to H by 2. So at mid depth we have column is equal to H by 2, and therefore we have pressure at point C will be equal to rho multiplied by G multiplied by column will be equal to H by 2. Correspondingly, we have the same formula for hoop stress. So we have hoop stress at point C will be given as pressure multiplied by diameter, that is the internal diameter, and is divided by 2 times of T. So all these values of the hoop stresses depends. In the case of vertical pipe which is filled with the water, since here it is filled with the water, that is a liquid, and in the case of liquid the pressure is given as rho into G into H. Out of that, the product of density and the acceleration due to gravity is constant, so pressure is directly proportional to the depth. As the depth will increase, then the pressure will increase, and correspondingly we have a hoop stress at the top will be equal to 0, hoop stress at the bottom will be maximum, and the hoop stress at point C is given as P multiplied by Di divided by 2 times of T. This time we have to take the pressure at point C, which is equal to rho into G into H by 2. Now longitudinal stress, on the other hand, is a stress that occur in the axial direction of the pipe, and it is caused by the weight of the fluid in the pipe and any external load. So if we neglect the external load, then we have a column of the water is equal to H, and it has a density equal to rho. So the rho multiplied by G multiplied by volume will be the weight acting in a downward direction. So let's consider only the weight here. The weight W is the weight of the fluid in the pipe, and this is same as equal to the specific weight which is equal to rho multiplied by G. Number of authors uses rho into G is equal to gamma also. So we have product of density multiplied by acceleration due to gravity is the specific weight, and the specific weight is normally expressed as Newton per meter cube. So you have to multiply by volume here, and we have a cross section area is pi by 4 di square. So let's multiply with the cross section area, that is pi by 4 multiplied by di square, and the length of this pipe is equal to same as equal to h. So you have to multiply by h. This total weight will act on the area which is resisting the weight W. So this is the cross section, which is enlarged cross section of the material that we are having between DO and DI, and this area is a resisting area. So let A represents here the resisting area, and this resisting area is same everywhere, and this resisting area we can calculate as circumference, which is equal to pi multiplied by di multiplied by thickness equal to T. In this case, the axial stress will act in a vertically upward direction. So this one is the direction of axial stress. Let's represent here the axial stress by sigma L. Sigma L multiplied by resisting area will be cancelled with W. So if we apply here the summation of Fy vertically upward positive, in this case we'll get the sigma L, that is the longitudinal stress or axial stress multiplied by area A is same as equal to the downward force that equal to weight W. So we have sigma L will be equal to W is equal to same as the product of rho into G. So we have rho into G into pi, and we have divided by 4 multiplied by di square multiplied by the total depth, because we are interested in stress at bottom, that is at point B. So you have to multiply by column H. If you are interested at C, then you have to replace H by H by 2. And if you at point A, then the weight will be 0 and the longitudinal stress will be also equal to 0, is divided by the area that equal to pi multiplied by di divided by T. So let's cancel out here some terms. Pi will be get cancelled, one of the D will be get cancelled. So we have axial stress, that is the longitudinal stress, will be same as the product of rho multiplied by G multiplied by H. Rho multiplied by G multiplied by H is same as the pressure at point B, is further multiplied by di and is divided by 4 times of T. So this formula is almost same formula that we have used previously also. The product of rho into G into H is same as the pressure at point B. So we have pressure at point B multiplied by di divided by 4 times of T. The same formula that we have used in the case of thin vessel also. But this stress is a different value as the depth will change. This value we have calculated at point B. If you want to calculate point C, then you have to use in the weight formula depth is equal to H by 2. So we have weight of fluid to point C will be same as equal to rho multiplied by G multiplied by pi by 4 multiplied by di square multiplied by H by 2, which one is again the pressure at point C, because pressure at point C is given as rho multiplied by G multiplied by H by 2. So the same formula will work here, only the pressure you have to take where you are interested to know the axial stress. And at point A, we have pressure is equal to 0. If the pressure is equal to 0, then the longitudinal stress at A will be also equal to 0. So there is no stress, neither hoop stress, neither longitudinal stress at the top point, and we have maximum value of the hoop stress and the longitudinal stress at point B. So if you have given the value of SYT, then allowable stress you have to compare with the hoop stress at point B, where we have a maximum depth. Now in the case of pneumatics, we are using the pneumatic cylinder, and we have movable piston here, and these pistons are continuously moving outward. So when the pistons are moving outward, it means that we have longitudinal stress acting will be equal to 0, and we have a hoop stress will be same as equal to the pressure P multiplied by internal diameter di divided by 2 times of thickness. So if the ends are moving, in that case the longitudinal stress will be always equal to 0. Longitudinal stress equal to 0 in this case because the weight component will not act. Since the weight component is not acting, the sigma L will be equal to 0. A tall open top standpipe has an inside diameter of 2750 mm and the wall thickness of 6 mm. The standpipe contains water which has a mass density equal to 1000 kg per meter cube. What height h of water will produce a circumferential stress of 16 megapascal in the wall of the standpipe, and what is the axial stress in the wall of the standpipe due to the water pressure? You have to calculate your axial stress, and he has given the circumferential stress, and for that one you have to find out what is the depth h required. So let's consider here we have a vertical pipe having inner diameter is di, thickness equal to t, and at a particular depth here, let's say equal to h, we have the circumferential stress that equal to sigma h is equal to 16 megapascal. So let's say this point is equal to a point. So at point A we have pressure PA is given as a product of rho multiplied by G multiplied by the depth that equal to H, and the hoop stress at point A is given. So we have hoop stress at point A is given as product of pressure multiplied by internal diameter di and is divided by 2 times of thickness that equal to T. From this equation we can calculate pressure. Once we know the pressure at point A, we can calculate depth equal to H. So let's substitute and solve it. We have 16 megapascal is the value of the hoop stress. Pressure at point A is unknown. Diameter you have to put as 2750 divided by 2 times of thickness, and we have thickness equal to 6 mm. Solve this, you will get the pressure at point A. So we have pressure at point A will be equal to 69.818 into 10 to the power minus 3, that will be megapascal. Now we can use the first formula here, that we have pressure PA equal to rho into G into depth H. Pressure here we have taken megapascal, so you have to multiply by 10 to the power 6, that will be 69.818, 10 to the power minus 3 and 10 to the power 6. So we left here with 10 to the power 3. Value of rho is same as equal to 1000. Acceleration of gravity will be equal to 9.81 multiplied by depth equal to h. So solve this and you can find out the value of h. You will get the depth h equal to 7.12 meter. In the second part, we want to calculate the axial stress at the same location A. So we have axial stress, that is the longitudinal stress at A, will be equal to the pressure P multiplied by diameter di divided by 2 times of thickness. Pressure you have to take in this equation is megapascal, is 69.818 into 10 to the power minus 3, that will be megapascal. Diameter is 2750 and is divided by 2 times of thickness. Thickness is equal to 6. Approximately this value is 16 megapascal. But they will ask you what is the axial stress at the top, that will be equal to 0. A vertical standpipe has an inside diameter di equal to 3 meter is filled with the water to a depth of 5 meter. If the allowable hoop stress is equal to 80 megapascal, what is the minimum wall thickness of the tank nearest to the millimeter? And neglect the restraint that the base exerts on the cylindrical tank. So in this vertical standpipe, we have depth h is given, and we have depth h is equal to 5 meter. Diameter di is also given, that equal to 3 meter. and the thickness we have to find out, and the value of the allowable hoop stress is given. The hoop stress is maximum at the bottom, that is at point A. So we have a hoop stress at point A is given equal to 80 megapascal. First we calculate here what is the pressure at point A. The pressure at point A is given as a product of rho multiplied by G multiplied by the depth equal to H, and the hoop stress value at point A will be equal to the pressure at point A multiplied by diameter di divided by 2 times the wall thickness equal to T. We can replace here PA as a product of rho GH, and in one step we can calculate here what is the required thickness. So we have a hoop stress at point A will be equal to product of rho multiplied by G multiplied by H multiplied by di, and is whole thing divided by 2 times of wall thickness. Now this value of the pressure will be in Pascal. So we'll go for SI unit. So hoop stress will be equal to 80 megapascal is 10 to the power 6. Pressure we are using in the SI unit, so we have to use the value of rho as 1000. G will be equal to 9.81. Depth is equal to 5 meter. So this one is Pascal multiplied by di is equal to 3 meter, that is correct. And we have 2 times the wall thickness. So we have 2 divided by T. This time the answer of T will come in meter. So we have T is equal to approximately this value is 0.92 into 10 to the power minus 3. That will be meter. Approximately we can take this answer equal to 0.92 mm, or we can approximate this answer equal to 1 mm. The video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.